welcome back from Christmas holidays. So, hello everyone. Welcome to the distinguished lecture series of Max Planck Institute for the Science of Light. This is the most important lectures that are happening at our institute. And the session is also broadcasted via Zoom online and will be recorded and uploaded in YouTube later if you would like to watch afterwards. So it's a great pleasure for us today to have a lecture by Professor Blatt. He doesn't need introduction for many scientists and also scientists who work in quantum field, but just to have this very general sentence, his research is on the field of precision spectroscopy, quantum metrology, and quantum information processing. So Professor Blatt studied in the University of Mainz, and then he finished his PhD in 1981. That's the year that I was born. That came to my mind when I was reading it. So and in 1982, he could get a DFG grant and went to the US, to Boulder, and worked with Professor John Hall, that many of you also know him because of the Nobel Prize in 2005. He had many stays in the University of Freie Universität Berlin, in Hamburg, and some other stays in the US, until in 1994, he was appointed to a chair in physics at the University of Göttingen. And then, of course, the year after, he had a call from the University of Innsbruck to have him in Austria. Since 2003, Professor Blatt has also held the position of scientific director at the Institute of Quantum Optics and Quantum Information. So many of you know about this important experiment, which is one of the main achievements of the group, which is in 2004, the group could show for the first time the teleportation. And if you look at the publication, there are two back-to-back Nature publications by two groups, one in Europe and one in the US, and they both made it to the cover of the Nature. So I went through the prizes to just announce them, and then, well, the number is really large, so it's somehow every year there was a prize. I just named some of them very quickly, that we have enough time for the lecture. So. Yeah, there is a Herbert Walter Prize, Austrian Cross of Honor for Science and Art. There is a John Stuart Bell Prize, Humboldt Research Prize, Stern-Gerlach Medal, Carl Zeiss Prize, Erwin Schrödinger Prize, and so on. So we are very happy to have you here, and we are very enthusiastic to listen to your lecture. Thank you.
So thank you again for this very kind introduction, and thank you all for inviting me. It's a real pleasure to be here. I've never been to this new building. It's very impressive. Thank you for your time, showing me the experiments, and thanks for lots of discussions I already had. So I would like to share a few things today with you, what we have been working with it in Innsbruck. And the subject of today's talk is about, as you said here, quantum computation, simulations, and quantum measurements. This is one of the older workhorses. We'll come back to that a little later. So let me show you that I'm coming here actually with 4 hats on. So I'll show you a mixed talk with many things. So I'm, of course, working at the University of Innsbruck. This is the group that I'm working with, but also at the Institute of Quantum Optics and Quantum Information of the Austrian Academy of Sciences. We have a startup company. I'll come back to that in the end. And in the end also, I'll show you some slides about the Munich Quantum Valley that I'm working for over the last 2 years. So the idea is that we are doing simulations, computations, metrology. I won't have the time to go to the interfaces part I've been working to. We can just discuss this maybe in the discussion section. The menu of today's talk is the following. In the spirit of a colloquium talk, I would like to start slowly by just introducing to you what do we see when we talk about computers and technology, and we want to ask why do we want to have quantum computers, for example. Then we need bits and pieces, in this case quantum bits, quantum registers, quantum gates, and some realization concepts. And I'll show you how to do the quantum computation with trapped ions. The toolbox with ions briefly mentioned, and then I'll show you just a few examples, and if you have time enough, I'll show you how to scale this up. These are our sponsors, many of them, and of course, there's all the work that we've done here at the QUOQUI and the Quantum Optics Group in Innsbruck. I'll come back then at the end to the AQT part and the MQV part. Let us start with a few quotations. If you just look here, that's the ENIAC, the Electronic Numerical Integrator and Computer at Penn State in 1947. And you find in the Popular Mechanics magazine in the United States in 1949, which is only slightly older than I am. The calculator on the ENIAC is equipped with 18,000 vacuum tubes and weighs 30 tons. Computers in the future may have only 1,000 tubes and weigh only 1.5 tons. That's a pretty tough statement. I wouldn't be here carrying such a computer with me. But if you just look even at 1986, it's not that long ago. We are to be even more ridiculous later and consider bits written on 1 atom instead of the present 10 to the 11 atoms. Such nonsense is very entertaining to professors like me. I hope you find it interesting, entertaining also, and I want to keep you entertained at least for the next hour or so. Let's see how this goes. When we measure the progress in technology, especially about computers, we all know Moore's law. Moore's law was invented and formulated empirically by Gordon Moore, who is one of the founding fathers of the Intel Corporation. Initially, this is the green line, that was the empirical formulation that served later as the roadmap for the semiconductor industry. And the reason for that is if you really want to become faster, you also have to become smaller, meaning that you have to have a roadmap where to go for with the instruments that allow you to go smaller. So this served for decades, and this ends right here at about 2010, but it really rolls off at some time. I can show you that in a different way. These are data that I took from Rob Keyes, where I just draw how many atoms we need in order to implement a classical bit of information. This is micrograms in the 60s, but then it goes down, and if you just extrapolate that right here, it would have been around 2017 or 2020, roughly, how you do that, that a single atom suffices or must suffice to carry 1 bit of information. And we know already before that we have to invoke the laws of quantum mechanics. And in fact, you see these things are rolling off right here. And there's lots of papers about Moore's law and other ways of drawing that. In the end, we have to consider that, and we have to then ask the question, so why the heck do we actually want to use quantum mechanics for computers? Why quantum computers? The generic answer, of course, is there must be some applications in physics and mathematics that are valid to do this. But what are they? The entire hype that we still see today, or even more so see today, started in about 1994 when Peter Shor from AT&T came up with an algorithm where he could show if you do factoring of numbers with L digits, this would work much faster on a quantum computer. In fact, it grows only polynomially in the length of the digits as compared to the classical case where this grows exponentially. And this, of course, got some anxiety in some agencies who had to hide something or who have to send some secret messages. Could this possibly be, because this is the encryption relies on the fact on the sheer impossibility of factoring numbers in sufficient amount of time. And so the money started to flow. A little later, Love Grover from Lucent came up with a different algorithm where you could show the database search can be sped up by quite a bit, whereas on an ordinary database, you have to, on the average, query the order of entries in order to find what you're looking for. With the Grover algorithm, you could just speed this up and grows. You only need the square root of the number of entries. In fact, these are still the main algorithms that we have today. There's a few more, there's a handful of more, we can discuss this later. But more importantly, and this is right now a hot topic, it's the simulation of Schrödinger equations that was alluded to by Richard Feynman already in the 80s that now plays a major role in really putting things forward and developing quantum computers. There's something that is usually overlooked but comes more and more into light, is the way to use quantum machines, quantum technologies for improving measurements. This was already pointed out in that paper by the Weinand Group and many others. You can use, say, a quantum computer as an atomic state synthesizer tailored to a specific measurement task, and I'll show you one of the advantages later on. But also, don't forget that we now really revisit quantum physics with what I call the information-guided eye. I won't have much time to talk about this, and we can again discuss this later. We now look back with the notion of Shannon entropy, with the notion of error correction, quantum error correction, things like that, that enters in the quantum realm. And the question really is, what do we learn about quantum information? What do we learn about quantum mechanics from that point of view? So this is a very fundamental question that is always of great interest to me, and we can certainly I will just scratch the surface of that, and we can delve into that also in the Q&A part later on. So let's get started. What do we need? Of course, a classical bit is a physical object in state 0, 1, the proverbial switch that we see here, and the register that we have in classical computers is nothing but a bit row. On the quantum side, this is just a generalization. You're talking about our proverbial two-level system right here, which is depicted usually on a Bloch sphere. And the quantum information is, of course, hidden in these two amplitudes right here. We generalize that to a register, so we have L2 level atoms, which of course encode the 2 to the L quantum states. The difference arises here. So we have to write this down as a direct product, meaning that these two L states could be in a possible superposition, and that superposition has, of course, here exponentially growing numbers that describe that state. So in fact, the state has to be written down as a wave function which describes the entire state. Meaning, and contrary to what you see here in the classical row, when you just change something here, say the 1 to 0, the rest of the register could not care less. But if you change something here, because of this full size wave function that describes the entire state, you change the state of the entire system. And that is what really leads then what we call the quantum parallelism. It's then afterwards the computational pathways that interfere to produce the result. So when you just look at the wavy structure that we see here, say stones, of course you could always calculate the interference pattern from where the stones are put in the water surface right here. But on the other hand, it's a delocalized information. That interference pattern contains the information. This is where the interference produces the result. When you just look now at the number of qubits that have these waves, then this is just growing here as we see the doubling the numbers here every line. Then of course the computational pathways grow as 2 to the n. You know the famous chess example where you just put a rice corn on each field. This is an incredible number of pathways that interfere and conspire to produce the result. So the result is actually in the interference pattern that we have here. That has a mind-boggling consequence. If we just look at that, when you have 300 qubits, the number of these computational pathways that interfere to produce the result is bigger than the number of atoms in the universe. I don't know exactly what that means. Again, we can discuss this. I have a hunch what this alludes to, but this is in my mind still mind-boggling because it's hard to imagine how to control this, and we seemingly are able to control that and what it really means in the end. So let's go on. In order to do some information processing, we need, of course, gate operations. The first thing to do is, of course, single qubit operations. So we need to place the information or the initial information at arbitrary angles or at arbitrary positions, and we need to be able to rotate the Bloch vector here by arbitrary angles. This is what we call a single qubit rotation. More importantly, in order to make if-then decisions, we need the equivalent of the classical XOR operation, which is denoted here as a truth table, however, already in a quantum mechanical notation, meaning that this is not only needs not to hold just for these entries here, but it also needs to hold for any superposition. And that coherent controlled NOT operation is the equivalent of the classical XOR when it holds for all superpositions. The good news was already found in the mid-90s. This is already providing a universal set of gate operations. Once you're able to produce these with any system that you have at your hand, you're able to produce a quantum computer. And so we can immediately write down a blueprint for the quantum computer. We start out with a superposition. We have a quantum process, and we deliver here quantum superposition right here. And of course, the quantum process, or the processor, has to be cut down to a sequence of these single qubit and 2 qubit gate operations, not necessarily with the same angles, could be different angles, but this is the way we do it, and the computation is a sequence of gates. And finally, you have to produce a classical output, because in principle, you could just reverse this. It's a unitary operation. You could reverse it. You have not gained anything. So you just produce it forward, but then you have to produce a measurement right here. You have to project things. And a projection gives you maybe one example of this one, maybe that one. You have to statistically measure that repeatedly and finally get the result of your computation. So that's the blueprint that we have at hand. And then we have realization concepts. So if you're going to go back to read some of the history of that, you find there's the first American-based roadmap, which is not continued for some time now. And there's the European map, which is continued. It has some information which is valuable, but this is up to date, and this is the latest version of it. I will talk about ion traps today, but there's many concepts that we have seen over the last 2 decades that have been tried out. Neutral atoms and traps of all varieties, atoms and cavity QED, NMR and liquids, superconducting qubits come in very many flavors, charge, flux, phase gates, and phase qubits, solid state concepts, spin system, quantum dots, and so on, optical qubits, linear optics, quantum computation, even electrons on liquid helium surfaces. There's a recent company now for the spectral hole burning, and many more things. In any case, these are all quantum systems that can be perfectly controlled, perfectly in quotation marks, as good as you can, and manipulated. And that's where the variety sits in. Over the last 2 decades, I think it's mostly these 4 that are currently preferred and are worked on. It's ion traps, neutral atoms and traps, superconducting qubits, and to a certain extent also solid state concepts. And I will talk today only about the ion traps because this would just take a long lecture. If you want to know more, I refer you to here the Quantum Manifesto. Some information is there. And there's one paper by the National Academy of Sciences in the United States, which is a bit US-centric, but still has valuable information. This is how it all started. This is the seminal paper of 1995 of these 2 gentlemen, Ignacio Cirac and Peter Zoller. They came up in 95 with an idea to use, say, single ions and traps sitting side by side, and having the ability to dress them individually with lasers, you should be able to manipulate that information. The point was that they figured out the idea to use the common motion to create the entanglement. This spawned quite a few papers later on. There's other great ideas here by these people, Mimar Sørensen, Milvan Sagori-Solani, Jonathan Plenio and Knight, and others. I'll come back to one of them. In essence, in this paper, they showed how to realize the C-NOT gate operation, meaning that you have a controlling qubit that controls the state of the target qubit. Keep in mind that has to hold for all kinds of superpositions. So that was the hard part, and they showed how to do that for the first time, and that started the entire stuff then already in 95. So let's start with the qubits that are involved in ions. For a qubit, as we have seen before, we need 2 level systems. These 2 level systems can be realized in many ways, with atoms, as we well know. We talk here about the optical qubit when we use, say, the alkaline earth elements. They have a low-lying D state, which is typically has a lifetime of several seconds. And then, so we can just encode that quantum bit in that transition right here. There's many more transitions available, of course, in the hyperfine qubits or Zeeman qubits, where you just have the 2 level systems encoded and low-lying levels right here. That works fine, and everything that can be done here in this stuff can be done by just replacing the 2 lasers with a Raman excitation. Otherwise, it works in the same way. And the ones in blue that are listed here are the ones that are predominantly used at this time for quantum information processing. I will be talking mostly during that talk about calcium-40. Whatever I tell you here can be easily translated to any of the other things. We have done that also with odd isotopes. We are using also barium, we are using strontium, but that doesn't really matter. So you choose your poison and you have to live with it. This is the trap that we have been working with. You saw that picture in the beginning of the year 2000. It's a relatively macroscopic trap. I'll show you other traps later. So this is the distance between the tips right here, about 6 millimeters, and the lateral distance right here is about 1 millimeter. And a trap really means you can confine ions there in a harmonic oscillator. And all that you need to remember for the rest of the colloquium here is the trap frequency, because that specifies essentially the harmonic oscillator. The trap frequency along the longitudinal direction is roughly about 1 megahertz, depending on the voltages that you apply, and in the lateral direction is about 2 megahertz. You see the frequencies written here. This is a typical trap. Very many people are using this trap these days. Bear in mind, when we started this in 95, there were only 2 groups in the world dealing with ions. Now there are about 100 groups in the world dealing with single ions doing quantum information processing. Back to the Cirac-Zoller idea. Now we know we have quantum bits to have a quantum register encoded in any one of these transitions. The most important part of the Dirac-Solar idea is this state vector. What does that mean? So we have the ions sitting right here, side by side in a Paul trap, in a linear Paul trap, and we notate in such a way that we write down the internal degrees of freedom, that's the amplitudes of each ion being the ground state or excited state right here, times, that's the direct product, the center of mass motion, and we write it explicitly in 0. This is the Dirac-Solar idea. They propose to start out with a harmonic oscillator in state 0, the ground state. Why? The reason is the following. We want to realize this C-NOT gate operation. And so, for instance, choose this as the controlling ion and this as the target ion. How the heck should that target ion know that this controlling ion has an internal excited state when they are sitting just side by side? Dirac and Solar, and they propose to do the following. We just point the laser first to that ion. We map the internal state right here to a 1 of the center of mass motion. Then we go with the laser pointing to another ion right here, the target ion, and do a 2-pi transition only if and only if, one, we have a motion in the chain right here, and then we go back. Because once you map this to the state 1 right here, this ion just starts to move, and per Coulomb repulsion, the entire chain, they are coupled, start to move. So this ion can know there is motion, and I'll show you how to do this in a minute. And then you go back and restore the system. That's how they propose to do that. It needs, as I said before, individual addressing, efficient single qubit operations. Of course, small decoherence of all the internal degrees of freedom, the motional degrees of freedom, and of course, then eventually you have to realize the quantum computation as a series of these gate operations. So let's see. This is the workhorse as we have it now, further developed a few years ago. And if you want to know more about some of the results, we have even a later apparatus, but this is the typical result. You see that in the year 2013. This is a string that we can readily observe by the resonance fluorescence. We just apply laser light here to cool it and excite the system resonance fluorescence. Typical in the sense that it's not the best that we ever observed. This is what we work with every day, really. You can go up to 100 ions, but this is really something we work with every day. What is this ion? This is a calcium ion. The calcium ion has a ground state here is 1/2, and then the D5 state, which lives about 1 second. That is the qubit. When we want to measure it, we couple it to a dipole allowed transition right here, and since we have a single ion only that we are addressing or working with, then the electron, of course, can shuttle back and forth only once it occupies the ground state. Otherwise, if it's shelved, as Hans Dehmelt would say that, to the D5 state, it's not available to go back and forth, it's scatter light. And so this is what we call the electron shelving technique. Bright state meaning this is the logical 1 or a spin down direction. This is a dark state, is a spin up or 0 direction. And this is how we then, of course, see where the quantum information really is. We call this for further reasons and a sigma c, obvious reasons, a sigma c measurement. This was the basis for the proverbial detection of the quantum shuttles that we did a long time ago. And this is always underlying any of the detection schemes that we have. Let's recap. We have a two-level system sitting in a harmonic trap where the trap frequency is nu. Of course, now we have to write this down in a different way. The Hamiltonian leads to many two-level systems which are just different by this trap frequency. That allows us to tune the laser frequency to very many resonances. So for example, if you tune the laser here to this one, from the ground state with n phonons to the excited state with n phonons, this is what we call the carrier transition. The system predominantly decays, sometimes goes back and forth, but otherwise nothing happens. But we could also tune the laser to this one here. Then the system predominantly decays on this one and climbs down the ladder until it finally resides in the states n equals 0. This is preparing the ground state by optical pumping, as we all know, ground state cooling, and this is the the state that we need to prepare for the Dirac-Solar scheme. In that case, we are left with exactly 3 transitions: the carrier transition, the blue sideband, and the red sideband. The blue sideband adds a phonon to the chain, and the red sideband just subtracts one. In fact, this is the internal qubit, that's the internal superpositions. And when we do that on the carrier, and this, of course, allows us to manipulate the motion and the qubit, or we create the entanglement with this. And details you find in here, these papers. Now we are ready to do things. We have everything together. We have an algorithm which is broken down in a sequence of the 1 and 2 qubit operations, in simplest case, but that we call a quantum circuit. We do this mostly by the carrier, and in this case only by blue sideband transitions. We don't need the red sidebands on the various cases. I'll show you different things later. I do on these isolated two-level systems block vector rotations. And the measurements are happening by just tuning the system into resonance on the carrier and just scatter light to see how we are excited. But the point sample is something is here in order to measure, say, coherence in the system. We just have to rotate the Bloch vector or the Bloch sphere prior to making a measurement, and this is rotating, projecting, rotating, projecting. This is not as tomography. And then you get the fingerprint here, for example, for our belt states that we get here, and we can measure them easily and can determine everything that we need to know. There's also spectroscopic tools with parity oscillations, but that is not a matter of what we want to talk about today. Let's come to the toolbox. The toolbox is now very mature. We, of course, have the resonant manipulation with a global beam that we apply to everything. This is our rotations about the angle theta and about the axis x and y, depending on how we tune it. The fidelities are here, so there's a typical gate operations. Then we have individual local operations that we do by off-resonantly tuning the laser somewhere there, because this minimizes crosstalk if we are detuned. These are described, of course, by sigma c operations, and if it's more general, it's Z operations. This is now the entangling operation that we are using instead of the Dirac-Sola idea that I've just briefly outlined. We are using a slightly more complicated way of doing it, but that has a distinct advantage. We are using actually two photon transitions. So consider, for example, two ions in the ground state, which are different by these different frequencies here, the Trap frequencies. Then we just apply bichromatic light on the red and blue sideband simultaneously. And if you just look the pathways, you see there's 4 different pathways that lead from S, both ions in the S state to both ions in the D state, to create a superposition that would be a proverbial bell state. And if you just add these amplitudes, square them, like for every good 2 photon transition, they are first order Doppler free. So that is the dependence on the n number cancels to first order. In the Dirac-Sola idea, this is not the case. This is why we prefer to use this operation, and that works very fine and gives us high fidelities and in small amount of times. It's denoted by a 2 photon transition right here, so it's like a dipole-dipole transition. I'll come to the notation in a minute. This is already a universal gate set, all 3 blocks consigned. Again, it's slightly different from the one that we had originally, but this is more advanced. And in fact, we can do things more. We can individually address these individual ions as we wanted and do these things in parallel, or we can individually address also these ions for do entangling gates with Miniaturization. All of these things are possible. For the more mathematically inclined here are the unitaries. So you see the local Stark shifts that we're employing here. This could be collective Stark shifts, and we note this all with these boxes. These are the circuits, and of course each underlying box is of course a unitary operation that we have here. This is a collective local operation. Of course, this is even more generally written down because it could be any superposition in this form. And this is a dipole-dipole interaction I alluded to. This is why we denote it as S squared. This is the entangling Miniaturization operation. And of course, we have many more operations right here. We can actually hide, say, one of the lines. This is the qubit lines. So we can reduce or enlarge the Hilbert space or a computational space at will. We have dephasing operations for open systems. We have initialization reset operations. We even can use some combinations of the internal degrees of freedom of the ion to produce a quantum cache memory, saying we can just store the information of one qubit in some excited states and do operations on the entire register while nothing happens to that particular qubit. And this is all done now. It's an overcomplete set of operations that we have, meaning that the system is now doing the following. We have to describe this with all kinds of sets that we have here, but otherwise it's the same. The measurement is again the same. It's just a more general set of gate operations that we have. But now, of course, if you have an overcomplete set, that means that these things are not unique. So what do you choose for a certain algorithm? And for this reason, we have come up with an optimizing compiler, what we call a multi-qubit coherent operations. And according to the author, a PhD student, Esteban Martinez, we call this the Estebanizer. And the stabilizer starts from a set of operations that we have available. Of course, in the computer, this is described as a unitary operation. So we know the unitary operations. The task at hand is, this is the algorithm that we want to realize. Let's just take a unitary operation. We can also do non-unitary things. It's not so easy, but we can do that. But then the task is to break this down in the appropriate sequence of these gate operations that is now to be optimized. If you just do this as you write it down, there are very many operations that are, of course, superfluous. So we have to avoid these things. And this is done now in the following way. We just start out with a set of local operations. That's probably not good enough, but that's good to start with the input state, for example. Then we try to describe that unitary with the first layer of one entangling and a set of local operations right here. And if that's not sufficient, then we go ahead and add a second layer, and we just go and try to describe this. This is brute force search at this time. There's no machine learning involved. There's nothing there. It's brute force because we have a limited set of operations. This is, of course, not scalable. If that were scalable, then you would have solved, of course, your quantum computer problem. But it serves to create what we call subroutines or sub-procedures to optimize them that we use as building blocks and stepping stones for the next things to do. And we can optimize this for runtime, we can optimize this for fidelities, we can optimize this for, say, certain coherence optimizations that we need, whatever you have. And in the end, what comes out is the unitary, that's the program that you have right here, as a sequence of the available gate operations. And this is changing all the time because we are adding to our toolbox. But it's always underlying. Just to give you an idea, when you do a so-called Toffoli gate, which is a controlled NOT gate, it's also available as a Toffoli gate in classical computation. You have to implement this usually in brute force way with 60 NOT gate operations, which is of course expensive because they are taking a little bit more time and of course they're more error prone. But if you just run it through the compiler comes up with a sequence that consists of only 3 entangling ones and many local ones. I would not have guessed this. This was not so easy, right?
Can I ask a very basic question?
Sure.
So you have a wave function that's a superposition of different states, and all these ions are supposed to be coupled to each other, but you usually show the fluorescence image, which one is in the shelf state or not, or whatever. Where's the phase information from that? How do you actually...
Of course, the phase... Thank you. The phase, of course, the wave function is set by the initial state, and then, of course, the first laser pulse sets the phase reference. And the last laser pulse of your algorithm closes that phase reference, and then you make the measurement. Of course, in the measurement, there's no phase involved. You just see the population. And you know, of course, from the programming, what the phases are. You could track these phases. And of course, you would have to, and we come back to that in the task we do later. When we do error correction, you have to keep track of these phases. But the starting and closing laser pulse for a certain algorithm, during that time, you have to keep the phases intact, or you have to control them. That sets the phase. So if you cannot...
So if you screw it up, you will see that your measurement is different.
Precisely, and I'll come back to that later. You have 2 kinds of errors. You have flip errors and you have phase errors, and you have to correct 2 of them. Right now, we are not considering that. We are just relying on the fact that the phase stays stable. Okay? But in principle, you're right, you have to correct for that. But in the measurement, there's no phase information. But this is just now about the gate optimization, and if you have, say, if you don't care what the outcome of this line is, you can even shorten that one. So you really tailor the system to what you have at hand, to the problem at hand. So when I talk to people right now at Munich Quantum Valley and say some people who want to apply this to a circuit, we don't want to know what engine is below there. We just want to have an agnostic program. I don't care what you do. I don't care what the hardware is. I can simply tell them, sorry, this is not what you want. You want to run an algorithm, you want to get a result. You better know what your system can do best. So you better know about your engine. So please don't come and ask me, I don't care about the engine. You care about the engine. And if you don't care, don't talk to me. Okay, so this is where the engine really is. This is a big optics lab, as you've seen it too. This is one of our optics labs, and this is where the trap really resides. This is the vacuum system. It's in a big magnetic shield, and this is how it looks like. and there's a bunch of lasers around, and that's all controlled from that point here. You know that. All of these algorithms have been done. I don't have the time to go through them. I just will show you a few examples that we have been working with. The ones in yellow are the simulations and the metrology part. Let's just delve into that one. And here, let me just show you all this that you've seen before has now been cast in two 19-inch racks. This is the work of the last 4 or 5 years, starting with the Flagship Initiative. And so we have now put everything in there by these two gentlemen, Christian Marciniak and Ivan Pogorilov. And this is the new paper that came out about 2 years ago that describes the content of that. And that's how it really looks like in the lab. This is a big consortium of people we've worked with, and this was set up in Innsbruck, and is now the basis and the workhorse of what we are doing in Innsbruck. The entire trap unit is down there. That's all there is. The rest is laser and optical control and everything else. Let's go to certain tasks. Suppose you have a problem to compute which is forbiddingly difficult to work on a classic computer. You want to go to a quantum simulator, say an array of atoms or a string of ions or superconducting qubits, whatever you have. Then there's essentially 3 procedures with which you could do simulations. The first one would be the simple analog simulation, so you just have a Hamiltonian that describes the problem right here. You imply this by applying this, say the appropriate laser sequences to the system. I'll show you that in a minute. And then you let the system go, develop it, evolve it, and then at a certain time t, you simply measure that and see this as a function of time t. But it requires, of course, an engineerable match between the interactions and the model, so you have to make sure that you can really rebuild this system in such a way that that you can actually implement this. The more quantum computation like simulation would break these things in pieces. So you just replace the entire process by what I've shown you before, by a circuit, by a quantum circuit, which is just a sequence of these unitary operations. But it requires very many gate operations. And there's now a hybrid way of doing this. So you just take a classic computer that writes down the Hamiltonian and then figures out certain parameters that tap into the Hilbert space of a quantum simulator, or say a quantum register right here. You really want to reach into every nook and cranny of the Hilbert space. You make only one measurement. So for example, you measure an expectation value and feed that back. The computer just calculates whether that expectation value meets the expectations the computer had with the parameters theta. If it does not, then it reiterates the thetas and goes around. Otherwise, until it matches, and then you have found the right value here. This is what we call a variational approach. All of these 3 things are currently used worldwide, and I'll show you just a summary of these things. The digital approach, again, is just using the sequence of gate operations right here. The difficulty is usually when you break down the Hamiltonian into parts like that, they do not necessarily commute with each other. So you have to approximate this by the so-called Trotter-Suzuki approximation, meaning that you apply the individual Hamiltonian's time slices, which are times t divided by n, then apply them of one after the other, and then repeat the entire cycle, the so-called Trotter cycle, many times. And that approximates this unitary evolution quite well. I'll show you some in a minute. And there's also a review here that you can see these things. The analog approach is usually done with ions in such a way that you, for example, apply what you can engineer in the lab. That means, for example, when I just a bichromatic excitation from the side, then I'm dealing with a motion which is transversal right here. So it's not a longitudinal, it's a transversal motion. Then you see immediately the bichromatic excitation is what we saw from the Melmer-Sørensen gate operation. It's a sigma x part, so which has a coupling constant Jij's. And if I detune the system, I add a Stark shift. So this is immediately writing down the Ising Hamiltonian. And just by doing this for a certain time, you can just see how the evolution goes and figure then out how the system behaves. These interactions can be adjusted with the drop parameters and other things right here. And if you want to know more, I have to refer you to this recent review by Chris Monroe. Just to give you an idea, this is a simulation that we worked out about 11 years ago. So you see a 4-spin system, and this is now digitized with Trotter steps. And you see it nicely describes the dynamical behavior of the system as the 4 spins. But you also see here the experimental points are the dark ones, and the open squares right here is what we expected from theory. So after a while, right here you see that we are running out of steam. The reason for that is we have so many unitary operations, and each unitary operation, of course, has errors. It's not perfect. And these add up. We do not do any error correction in this system. So this is why we are running out of steam. You have to improve, of course, the gate operations to a point that you can actually do this. That depends, of course, on how many you actually need to do this, and this is the difficulty. But on the other hand, it's widely applicable to many body Hamiltonians, and we are still working on that. We have also done this with a lattice gauge theory in a fully trotterized version. So this is a rewritten lattice gauge Hamiltonian in a sort of spin notation that was handed down to us by the Solar Group. And we, of course, have broken this down into a sequence of these gate operations. So this is about 220 gates that we repeat. And we can actually see that what the Schwinger model describes is a pair creation process right here. So a pair gets created right here. Particle-antiparticle pair, and this matches really exactly with the expectations. And we are currently working on more advanced things. This is, of course, one-dimensional QED. Right now, we are trying to do this in 2 dimensions. The really interesting things come when you can do that in 3D and even for other coupling constants. Then there's analog quantum simulations right here that have been pioneered also by the group of Chris Monroe. They see the using Hamiltonian again. They could just see crossover from paramagnetic to ferromagnetic behavior, the Néel ordering, and see the phase transitions right here. We have done this also by seeing the ballistic transport, for example. So we just create one spin excitation right here, apply this is the same Hamiltonian, just where the B term is much bigger than the JIJs, and then it really goes to this hardcore hopping boson model right here, and then you see how this interference is happening and how entanglement is created. So you see really how this is, how the entanglement progresses through the entire system. Or we have done more transport simulations. So you see here ballistic transport as here. We can see Anderson localization. We see diffusive enhanced transport. If you just increase, say, the noise right here, the noise figure, instead of the disorder right here, and we can, if the noise is even more prominent, so bigger than, of course, the uncertainties right here from the disorder, then we get a diffusive suppressed transport by the quantum Zeno effect. And in fact, we have more recently studied this also in a hydrodynamic limit to see that there's hydrodynamic behavior, Levy flights, and things like that. There's a myriad of things that can be done. Let me just tell you a little bit about the variational quantum simulations right here. This is for finding essentially ground states. It's a bit more difficult to use this for dynamical behavior. It's mostly used for steady state solutions. This is where we really have parameters, and this goes all the way around until we match the expectation. This was again done for the lattice Schwinger model. And you see here in a plot that I call a Flagship plot because there's lots of points right here. In the end, you have to follow them very closely. And this is just the number of iterations. And eventually, this is the energy that we figure out when we just measure iteratively this expectation value. There's many points right here. Why is this? The reason for that is the algorithm that does this determination, whether this fixes this, of course, has to look whether there's a global minimum somewhere in the hypersphere, the hypersurface that you get there. And you want to avoid that system gets stuck in a local minimum. So you have to have a stochastic component. And this is why this is sort of searching for, say, more global minima. And eventually, the closeness is described right here to the final result by these numbers right here. And eventually, you have to stop right here. The difficulty is, of course, the stopping criterion. Of course, you can measure forever. Did I reach actually the minimum? You never know that precisely, but you're coming as close as possible. But the good part is, instead of evaluating an expectation value, you could also evaluate, of course, in the classical computer, the variance. It requires a few more measurements, but once the variance is very close to 0, then you know I've found an eigenstate. So it's a sort of a self-verifying procedure, and this is the good part. We've demonstrated that as well. We can also do this in quantum chemistry. Sorry, there should be an H2, not an H. This is H2 molecule, where we really can come close to chemical precision in the potential that we do this. The Monroe group has done this with water molecules and many other things. So this is all available, and these are all toy problems. The question really is, can we go to something that is, of course, much more bigger? Before I do this, let me just show you one application which I find really nice for doing quantum measurements. This is again the variational circuit, and this was an idea that was worked on theoretically by Raphael Kopriger in his PhD thesis in the Solar Group, and in our lab by Christian Marciniak and Thomas Feldka. What is the issue at hand? Suppose you want to measure, say, that frequency very precisely, say for a frequency standard. Then this would work with a Ramsey spectroscopy cycle. You just have this waiting time and see the phase evolution. When you do this, this is what we routinely measure in the lab. This is a nice Ramsey pattern. And if you go then to a waiting time of 5 milliseconds, you get even better resolutions. So typically, this is the latest result. This is what we get for this transition frequency down to about 10 to minus 16 in the Allen plots. We've measured that repeatedly because there was a discussion initially, and now we have corroborated that the later values are indeed correct, together with the PDP and others. This is a PhD thesis of Milena Guevara. And another question is, can we do better if we just take more particles? Because this was done on a single particle. This is the ordinary Ramsey part. But now if I take, say, for instance, say, many qubits, not only just 10 or 20, whatever, but I could do this in a more general way. This is just a single pi over 2 pulse. In principle, I could replace this by a unitary, what I call an encoding pulse, and I could also replace this by another decoding pulse, of course, with a different set of parameters. And then I could do the same thing as in the variational ansatz again. I just define a cost function. How can I make the system better? We have to define what better is, and I'll come back to that in a minute. But once we do this, then I measure the total excitation. I can just again vary the number of procedures that here are involved. So it's not just simply a pi over 2 pulse, but some more entangling operations right here. Or in terms of continuous variables, we call this a one-axis twisting operation, and so we just could really create squeeze state by that way, and this is precisely the underlying technology. But then again, we have the degree of freedom right here. For the analyzing pulse, we can also decode this, and we let this iterate, and we just find the optimal parameters. What does that mean? We estimate then the interferometer phase, because that's a Ramsey interferometer essentially, by the measurement record. We calculate the mean squared error. In this case, we make a Bayesian estimate with a certain prior, and then we measure the imprecision of the variance of the signal that we get and optimize the performance. That's the idea. Let's see how this works. When I just do now an ordinary Ramsey experiment, but in this case now the phase of the analyzing pulse is just shifted by pi over 2, so it's an x and a y pulse, which really means we have a sine instead of a cosine that we saw before. So this is actually the interferometer, and we want to stabilize the interferometer right at this point. This is the center. This would be the prior that I see, the distribution of the errors, because it's shot noise limited, and if I calculate the mean squared error, I get this funny shaped curve, but this is the input. Another question is, this is what I do with classical coherent spin state. That's a standard Ramsey, pi over 2 pulse, pi over 2 pulse. We don't do anything else but pi over 2 pulses. This is the encoding and the decoding procedure that's denoting things. If we now change it to a sort of a Melmer-Sørensen operation right here, remember this is the one-axis twisting operation that we saw before. This is sigma x times sigma x, creates a squeeze state. And that squeeze state minimizes the noise right here, so it goes down. As you can see that, it doesn't do very much in the wings right here, but that's fine. And the question really is, can we do better than this with this spin squeeze state? When we do this now, without the spin squeeze state as input, excuse me, but with the standard pi over 2 pulse, we just want to tailor the measurement. Then we find for the mean squared error, which also has a certain capture range in the system for the interferometer, that this actually linearizes things. The slope is not as tall, as big as it was before, but it's linear, and the capture range of the interferometer is bigger. And the error is not quite as way down as the spin squeeze stuff, but within the capture range, this behaves better, and this is better interferometer. But once we now let the system go for both the tailored input and the measurement, we see this is really like a big gain. We are down as well as for the spin squeeze part, even the parts below them, within the error bars right here. So this is the way to optimize things. The the one-axis twisting operation just shears the ellipse on the Bloch sphere, and then you just let the system go. But then, of course, it twists and gets a banana shape. If you just do a measurement like this, you get the ordinary measurement. But what this does, it adjusts the measurement according to this banana shape and really gets the optimum out of the system. In other words, when we just look at the gain that we get, this is the classical domain for the classical Ramsey features, then we see that here is the optimal quantum, and the red points are showing you that we are pretty close to the optimal quantum procedure, and we can gain about 5 to 6 dB already with the 16 ions. This is not many. If you go to 50 or 100, so you can improve a standard experiment that, for instance, does a frequency standard like this by 6 to 8 dB and more, which is already quite a gain, and you could think about the tailoring other measurements as well. Let me just, since we are running out of time, coming to to my conclusion here. The question is how to scale this up and to really go to bigger procedures. Now, scaling up means the following. Of course, we need more qubits, which really means we have to extend our traps from the 1 dimension that we have right now to at least to 2 dimensions. 3 dimensions with ions is a bit hard, but even there are ideas. We need more operations, better control. We need quantum error correction. I'll come back to that in a minute. We need more computational power, meaning that we need a tailored quantum problem. That's a key problem to solve. Nobody knows what that could be. Of course, we have key problems like factorization, which is not so important anymore. There are key problems like in chemistry and other things, which are way out. There's orders of magnitude that you need of gate operations and times. We cannot do this. So, for example, for a relevant problem in chemistry, you need about 100,000 logic qubits and 10 to the 12, 10 to the 14 gate operations that we cannot do at this time. So the question is, what is a key problem that shows that this is indeed gaining some speed and some information that you cannot get with a classical computer, which really needs to be identified. And what I personally, as an implementer, really want to have is predictability. What do I mean with that? Predictability for me means when we want to scale the system up, I need to know, of course, the component performance. How good is the fidelity of my 2-qubit gate? How good is my storage? How good is my readout and everything else? From that, I would expect when I scale this up and add, say, another few qubits to this, that I can calculate the system performance. And all of you who have possibly used the IBM quantum computer, who just do this, knows that this is just not the case. The system is usually non-Markovian. We have measured that. We have had some fights with some people about that because they believed this is all Markovian. There's nothing like Markovian here. And you have to figure that out in detail. And this is why we have a whole supercomputer in Oxford, Simon Benjamin, who really has a full-blown error model of our computer in his classical computer to see how this error propagates and how we can actually undo these things. This is, in my point of view, a very important part to get to really a scaled-up system. But we also need to scale down. Scaling down really means we have to go down to some space. We have to miniaturize the control hardware. You've seen already our first task. We've put everything in the 2 cabinets of the 19-inch racks. That's a good part. We don't need to control the entire lab anymore. We need protection schemes. Passive protection schemes are already implemented, but we also need active correction schemes, meaning error correction, and faster gate operations, because at this time, the gate operations are microsecond-ish. Unfortunately, I've developed a system which could do gate operations with ions in 100 nanoseconds, but I have to give up the lab. Unfortunately, we cannot do it anymore. Sorry, guys. If you want to know how it goes, somebody can build it up again. Scaling out is another one that's usually not considered. Scaling out really means we need interconnectivity. It's a modular design. We need optical interfaces with the hardware part, but also distributivity. So we need quantum parallel processing software. That doesn't mean that we continuously share the information over long distances, but we have to break the system down in parts that can be done here and there at various nodes and then be put together in a coherent fashion. This does not even exist at this time. So there's lots of these things that need to be done. I don't have the time to go through all of these things. In my group over the last years, we have tackled many of these things individually, and I could just talk about an hour of each point here, but let's just go to the scaling of the ion trap itself. This goes back to an idea of Dave Weinand, who said, okay, the Dirac Solar is too slow, even the Miller-Sørensen works fine, but it is slow, and in the end we have to make this in parallel. The idea is to come up with chip traps and microstructure traps, so we have storage regions, we have interaction regions, and we do this all the time. And so we have to scale down the traps from what we have here to miniaturized traps. These are traps that have been used over the last years with our collaborators in Mainz, Sandia, Honeywell, now Quantinuum. We have our traps here. This is at NPL, this is the PDP trap. And this is the vision that, for instance, Ike Chuang had many years ago. You could do that in parallel. This is a full-blown quantum error correction code by moving each ions individually, and it's a little bit like Star Wars on a chip. The good point is you can actually do this in parallel. This is still visionary. Some people do this. The closest who can do that in Germany is Ferdinand Schmidt-Kahler. He's very good at that, and he has very high fidelities. He can already do a full-blown quantum error correction that way. And the next question is, can we keep the qubit alive? Keeping a qubit alive does not mean we have the eternal qubit, the eternal memory, but keeping it alive at least for the time I take the system for a computation. That's what I mean with that. And I'm tackling this together with Thomas Mons in my group and Markus Müller, who's right now professor in Aachen, who does the theory for us. This works in the following way. It looks like a daunting figure, but essentially it's like bookkeeping. You could call it a color code. So we encode a single qubit into 7 physical qubits. And the idea goes as follows. In order to measure this right, we have so-called stabilizers, and these stabilizers have to add up to a positive value right here, all these measurements, and then you know nothing has flipped. And if you just go around, you can figure out from the stabilizers what has flipped, and then you can undo these things. In fact, you can encode the system with a sequence of pulses I've written here, circuit. You don't worry about this, it's a black box. In the end, we have a logical 0 encoded into 7 ions. That's the minimal instance CSS code or color code in this case. This is our logical qubit. So we have these 3 plaquettes that we have to do for the bookkeeping. And this calls immediately for a certain architecture. Suppose now you have a logical qubit encoded into the 7 qubits. In order to see where the error syndrome really is, in order to correct for this, you need 2 ancillas. But the ancillas could also be faulty, and this was for a long time, it was a difficulty that we couldn't overcome. And there was only recently in 2018, 2019, I'll show you the paper in a minute, the idea of Ben Reichert, we could add another flag qubit to protect things and to select things. But then the point is, then if you had, say, one logical qubit here and the next one there and the next one there, then the idea would be to make so-called transversal operations in order to implement gate operations. What is a transversal operation? If you have encoded your system into a logical qubit and you have the next logical qubit here, so now you want to make, say, a C0 gate between the two, then it very much depends on the procedure, how you have encoded, what kind of a procedure, what the algorithm really represents, then the C0 between the 2 logical qubits. And the code is transversal. Then, when this boils down to making the same operation between adjacent physical qubits all the time in parallel, though this would really make our lives a lot easier. If I use the surface code, the Kitaev surface code, who had maybe even a higher threshold, I could not do this. It's not transversal to begin with. But if I use the color code, and this is the reason I've chosen it, it is transversal, so we can make these transversal operations. And of course, this architecture is what's now underlying for, say, a 2D trap. And the first approach that we did was 2012, 2014. Unfortunately, we had lots of flaws. It worked, but not well enough, because we had shorts and the technical difficulties. It really goes down to the details. In the meantime, we have teamed up with Infineon, and we have cut back the system. We just wanted to go to 2 strings which are side by side and then extend them in this area. And without going to the details right here, you see that this works. We already have ions trapped right here. The distances are still too far away to get a good coupling, but the system works. And now Infineon is really working on miniaturizing. We have to cut down the sizes by a factor of 3. 30 microns is good enough to get us enough coupling across laterally, and in the longitudinal direction we can certainly go closer. And this has the big advantage that aside from, say, square lattices, we can just also do triangular lattices and things like this. And of course, the dream is to go to something like this, say 10 ions by 10 ions, and have 100 qubits in this sequence. And then you could do say 2D codes as well. So this would be the way to scale this up to a larger system. People are dreaming even already about 32 by 32 ions, but this is maybe some time off. At least we are working in the Trap on this, and Silke is one of the PhD students who works in Villach with Infineon to do this. We have a group already at Villach working these things out. Okay, this brings me to the end of my talk. Let me just give the very latest. We have, in the meantime, last year for the first time, achieved a fault-tolerant universal gate operation. And this works as follows. So the difficulty is when you just do these plaquettes right here, and you measure the stabilizers, it's always these 4 measurements, X or C. Then the difficulty is that there could be error propagation in the wrong way because your operations are faulty too. There's always a back action. The controlling not really means here, for example. You always assume in the simple case that you don't do anything right here, but you just control it right there. But of course, if you do not that perfectly well, there's a back action, and that propagates the error in the wrong direction. Then you get 2 errors which cannot be corrected with a color code, because that can correct only for 1 arbitrary error. And Ben Reichert, as I showed you before, came up with this protocol where he said, okay, we can just add another flag that checks whether the propagating error has occurred or not. And then we can discard these things, and then we just have a very clean encoded qubit right here. This really made it possible and spawned a number of papers. I don't want to go through this. Over the last 2 years, it just exploded in various groups. We have now fault-tolerant implementations, and I'll show you how this works in principle. So what we do right now is we have a non-fault-tolerant state operation, and in case then the error propagates in the wrong way, we have a checking here with the flag qubits, and once the flag is red, simply we discard it. If we don't have a flag that is red, then we say, okay, if we're successful, and we do that. Typically in our implementations, the flag gets raised in about 10% of the cases, so we are discarding 10% of the cases, which is, we can do that. Of course, it's not ideal, we have to cut this down, but at least it is something to work with. And you see how this works. This is what we theoretically expect. This is what we experimentally get from the plaquettes. And we do a second round right here. These non-correctable errors, they are significantly reduced to a fraction of a percent. So this is negligible. This can be worked out. And in fact, we can do a full-blown fault-tolerant CNOT gate operation. So we just have 2 qubits, 2 logical qubits. We do everything right now in a parallel fashion. We verify it, then we do the controlled NOT in a transversal way on each single qubit in parallel. Unfortunately, the diagonal terms are a bit more faulty, but in fact, we get a fidelity of about 75–76%, which is not super good. But it's the first time that we have a fault-tolerantly encoded qubit entangled with another fault-tolerantly encoded qubit. So we have 2 logical qubits that can be connected with transversal operations. And more importantly, for a full-blown logical set, we need also a T-gate. This can be done in transversal way. Unfortunately, even the color code does not allow to do this T-gate operation in a transversal way, and this has to be injected. This is a huge procedure, so you just do the non-fault-tolerant encoding. You make an eigenstate of the Hadamard operation right here in a transversal way, check whether the flag has happened, then you have the error detection and the 2 qubits right here, and then you just inject it and you get the magic state with a fidelity of 99.4%. This is the first time that you can do this. So we have a full-blown set for logical qubits. And this is the starting point. Of course, we are far away from really getting this into action because we need to do this now all the time with full-blown error correction so that it self-sustains it. But this is the way to encode it, proceed it, just to let you know how complicated these things get. But they can be done and they can be reliably encoded. Let me conclude. The dream is, of course, that we use a bunch of ions. Many years ago, I dreamed about doing this with 5 ions. Right now, we are at 10, and probably the last calculations show we probably need a 17-qubit color code plus a few ancillas, so it's more like 20 ions per logical qubit at the least, if not more. But then they can be interconnected by dipole-dipole interaction on a chip or even cavity interfaces. We've done part of that already. And then, of course, you can go through all the systems. We need more qubits. We can go up to 100 in the current setups, better fidelities. Development of the trap arrays is right now onboard addressing onboard electronics with Infineon, even onboard optics. That's miniaturization. All of these things are highly technologically involved. And we still are in need of looking for characterization procedures. This is still a problem. The bigger the systems get, the harder it gets to characterize what is the entanglement, what they can actually do. And of course, as I said before, this is what I call the holy grail. This is something we need to overcome. We have to keep our qubit alive. And then everything else, it's not exactly peanuts, but this is what you can do. And so this is where we are working hard. This is the team that has been working over this over the last year. The group is still pretty big, but we have very many seniors that actually took over. But anything would not be possible without the help of very many theorists, among, of course, them of Peter Zoller, the most dominant character right here, but all of the others contributed enormously to that one. With this, I'm ready, and I wanted to show you where we are. This is the quantum computer made in Tyrol, also by our company, Alpine Quantum Technologies. And this is how it looks like. This is a commercial product. This is not something that I'm just a flyer that I'm advertising and you can do this maybe in 5 years from now. No, you can buy it. Go to Thomas Mons. This is ready. We have 2 machines up and running and they're on the cloud accessible. So if you want to calculate on these machines, contact Thomas or contact me. We get you access for free. And you can do these things. We are proud to have this made in Tyrol by AQT and it's available right now. And this is the, sorry, this is my salesman pitch. I'm not good at that, but it really is available. Usually people don't know that. They go to IBM, they go to everywhere, but these things are here. There's 50 plus qubits. We have 24 qubit proven entanglement. We have done everything from Shor's algorithm, as I showed before, even some financial case, some security chemistry cases, whatever you want. This is the interior. And this is the quantum CPU that used to be in a big optical table. It's just 50 by 50, 50 by 50 by 60 centimeters, that's it, including magnetic shielding and everything. That's all there in a beautiful way. With this, I'm ready with my talk. Let me conclude with a few slides about Munich Quantum Valley. I'm running over time, I know it, I apologize. But I'm only at 2 minutes over time right now. Munich Quantum Valley, you have heard about this, is now a registered association of these 7 partners. Erlangen is among them here at the Friedrich Alexander University, but also people from here are, of course, in the meanwhile, participating. And the idea is that the Munich Quantum Valley establishes quantum computation and quantum technologies in Bavaria. This is based on 3 different platforms. We are starting out with atomic qubits in the group of Emanuel Bloch, the superconducting qubits in the group of Stefan Philipp at the Technical University, and we will provide some quantum computers on ion qubits. We don't do the manufacturing in Munich, but we provide them with the Leibniz Rechenzentrum. The entire idea is planned around the so-called quantum computer stack model. So we start out with the platforms right here. There's hardware adapted theory right here. This is the interface of the qubits and the classical and quantum control. There's the architecture and the platform topology, system engineering. This is Fraunhofer essentially. Then we go up to the software part. Of course, these things are always sitting on the interfaces. They're not exactly limited to the individual stack structure that we have, up to the applications that we have here. And the people that are using that, you probably know most of them. So if you want to contact them or you want to collaborate with them, please contact them, contact us. You're welcome to contribute to this, because it's a big enterprise that's at this time coordinated and managed by me, where we really try to provide the infrastructure, the know-how, and we want to really coordinate things to get everything together, to really have, maybe in a few years from now, the quantum technologies available for computation. But this goes on because we really want to contact things also with so-called lighthouse projects. They are now active just with the beginning of the year. These lighthouse projects are supposed to be complementary activities to the consortia activities that we have here. where they jointly should provide what we want to have, the quantum ecosystem in Bavaria. And this is a list of the recent lighthouse projects, among them, of course, the quantum communication infrastructure led by Gerd here from MPL in Erlangen. And so contact any of them, just work with us. We really want to bring it off. We want to have quantum technologies at large in Bavaria, and this is what I'm here for. With this, I'm just showing you the roadmap. We've promised in 5 years to have a NISQ quantum computer technology available with up to 100 qubits, excuse me. And then from there, we start the development of fault-tolerant computers such that the program, and I'm planning not just to the end of, say, 26, but the current program runs, that we have something available until 2030 and beyond, because when we invest 300 million euros in Bavaria, this is not over in 5 years from now. We want to continue this, and for this we also need your cooperation, your collaboration, and your help with this. With this, I'm ready. This is my Munich Valley Munich Quantum Valley part, and I hope I have entertained you a little bit over the last hour. Thank you for your attention.
Okay, thank you very much for the fascinating talk. I assume there are questions from the audience.
Either among friends, if you were to put your money, on which technology would you put it?
Among friends, I wouldn't even put my money on a single technology at this time. This is why Munich Quantum Valley pursues the 3 technologies that we have the expertise in Bavaria. It is very difficult to say that. See, the difficulty is, as I told you about the scaling up part. In the end, you have to control that many logical qubits. As I said before, choose your poison and you have to live with it. If you do it with the ions, they are ideal because they're all the same. Atoms, they're all the same. Atoms are right now very good in forming, say, 2D arrays. The difficulty with them is the range, the connectivity is a limit to a certain extent. But the superconducting qubits, you actually think you can actually scale this up, but there's just nearest neighbor interaction. With ions, the connectivity is all to all. So it's hard to compare because in the end it comes down to the point, what kind of a goal do I have to achieve? What kind of an algorithm do I run? Some of them, like if they're optimization algorithms or say some sorting algorithms, they don't need the connectivity. Others need the connectivity to speed up. I really don't know. Frankly, I don't know.
Thank you.
Okay, next question.
So you mentioned that your operations typically take like on the order of 10 microseconds, and your coherence times, like optical coherence times, are on the order of a second. So that leaves you with 10 to the 5 operations you can do.
Yeah.
Is that fundamentally enough for like any calculation that you want to do, or is this at some point like a big hurdle that one has to overcome?
That's precisely the reason we are doing quantum error correction. Because with the quantum error correction, you can correct for the errors, whether they are phase errors or flip errors. That's what I mean by keeping a qubit alive. Of course, for a certain time, for a certain extent, you can keep do these things maybe for a few hundred qubit operations. You're fine. But then you accumulate errors, and then you have to correct for them. And then the question is, how often do I have to correct? Do I have to do this every step? Then it's time consuming. This is the brute force error correction as we hear about it. Or can I just protect these things for a certain while and still keep track of the phases that maybe go wrong and then correct all at once? So there's different ways of doing this. But what you're telling me is essentially, okay, I have to keep track of the phase for the entire computation. Yes, I do. And so I better know what I'm doing there to begin with. I cannot simply blindly do 10 to the 5 operations, then you would get nothing. This is exactly what happens when some theorists right now run without thinking a sequence on an IBM quantum computer.
Yeah, fascinating talk. Thank you.
When you told us about, so you showed the various ways to approach the problem. One of them was finding a ground state of an Hamiltonian.
Yes.
Is this the same what annealing is?
It is sort of a variant like the annealing, yes. It is, it's not quite the same as say, D-wave operations, things like that. It's simulated annealing, and the way they do it, it's actually more like a QAOA, so a quantum approximate optimization algorithm. The annealing works in such a way if you have very degrees of freedom, so you just slowly change the various, so you adiabatically follow what happens there, and then you determine things. But even in a D-wave computer, this is never really fully adiabatic, because they have so many qubits, what they call qubits, that they would have to be so slow that they don't see anything. So the truth is somewhere there in the middle. But we are closer to a QAOA operation.
And another minor question, you said that the factorizing is not so important anymore. So you say this because the RSA, there are competitive ways to create public keys, so you
yes.
can buy this is why you said this, right?
No, at this time, I think RSA is still safe. And the reason for that is because at this time they are using, to be safe, RSA 2048. This is a huge number, and there's just no way we can crack that in the near future. And they can easily go to 4096, for example. So that's fairly safe for a long time. But these people are thinking about something else. If you're encrypting something that has to stay, for instance, in the archives in Ehrenbreitstein, so for 30 years, how does anybody know whether somebody comes up with a machine in 20 years that could crack that? It's for the short-time communication, what we have, everything is safe. But with these long-range things and the BSI in Germany, they're actually thinking about twice the security times. So it's more like 50, 60 years. They are worried. And it's hard to say. I'm not so much worried about that one because there's other procedures. Right now, there's encryption with they call it post-quantum encryption that works on elliptic curves and other procedures that are so hard that even with quantum computers you cannot crack it. And though there's ways out of that. Who knows? Yes. Okay, I agree. But at this time, I would not so much be worried about that. And also, if you just look at it, in order to be competitive, say with an RSA 1024 number, you would roughly need on the order of about 100,000 qubits and a huge amount of computation time to crack it. There was a recent paper, I don't know whether you've seen it on the archive, by Chinese people. They claimed to have solved the factoring problem by minimizing that. And the factoring problem is factor x times y is a certain number. Now, the point is, if you want to have the factors, you could actually do the following. Take x times y minus n and look for the minimum. So it's an optimization problem. And then they just went to a QAOA, procedure variational ansatz, and they figured out, yes, they can do that, and they can solve a few things more than what people have been done. We have done number 15, 21, and things like that, and others have done 100, whatever. But not big numbers. They claim to have done much larger digits, and of course there was excitement for about a week or two. And then people then slowly learned that of course QAOA is actually exponentially hard. You don't gain very much with that. In the end, for large numbers, there's no danger at this time. And for the encryption for RSA, there's these post-quantum measures. With Munich Quantum Valley, for that reason, we are organizing in May one symposium together with the University of the Bundeswehr in Munich. A symposium, one-day symposium. If you're interested, let me know. On quantum computers meet cybersecurity, where we put these things together. Harald Weinfurter is on this, and so we are trying to do this to evaluate where is a possible danger, to really bring the communities together.
Okay, so I'm afraid in view of the time, I think it should be
best to stop at this point, although I see there are still many questions. Maybe you can...
If you have questions, just approach me and then we can discuss this personally.
At this point, I would say let's give a round of applause to Rainer for the beautiful talk.